start.
You all right over there?
It won't let me use the call. It's impossible.
It's not impossible. Yesterday's was kind of a mess. I thought maybe starting fresh might be a little bit better. So here we go. So you said part C you have a difficulty with, so we'll take a look at part C. Are there any generalizations we're able to make about the square loop that could help us solve this problem? Yes, sir?
They do say that the magnetic field between the two circular loops is uniform in the region of the squares.
Excellent. So that statement's important because I want to make sure you actually understand that the magnetic field here, say, would not be the same as the magnetic field at the center. It would be different and in a different direction. Now, by placing two loops close together, we do get a more uniform field, but it's not going to be perfect there. So they're allowing us to make a generalization. And that generalization is that the magnetic field is uniform in the entire region where the square exists. So you might be surprised, but calculating the flux isn't all that tough once we know that. First, we did have an expression for the magnetic field. We don't need it here. Determine the magnitude of the net magnetic field B net at point P. It says in terms of B net and S, determine the magnetic flux of the square loop. So question C does not require that you use what you have from question B, even though we did painstakingly derive an expression for half of the magnetic field that exists at that point. Putting two loops there is just going to double the size of the field. So that would be your answer to question B. Multiply by 2, because there are two contributions to the magnetic field and they are in the same direction. So for C, quite literally, magnetic flux is just this product. And we know the magnetic field is a constant everywhere where the area exists. So all that's left for us to do is say B net. You can factor it out. It's a square loop, so that's it. Yep. I don't know that we have all the information to do D. In fact, yeah, I didn't expect you to be able to do D, I guess. Oh, I know. You need Faraday's law. Yeah, and we haven't done Faraday's law, especially not for a rotating system. So we would have to start from a place where we don't have a good place to start. Faraday's law is the induced EMF, which is a voltage that's created due to a changing magnetic flux. So C is kind of where you have to tap out right after C. But it's not particularly hard, except that you need to calculate the rate of change of the magnetic flux, which in this case isn't actually a difficult thing to do. We have an angular speed, but it's what's changing that is hard here. The magnetic field is constant. The area is constant. It's the angle. So we will get to this. This is our next topic, is induction. So the moment we test out a magnetic field, so we're going to be going here. What?
If the currents are both going like that, what one's all the top? How do they reinforce each other? Is it?
You want me to do the right hand rule for you?
Yes. I'm probably doing it wrong.
It's okay.
I was confused about it earlier.
I'm going to draw a different picture to help with this. So let's take a look at the bottom loop first by just drawing two circles. I am cutting through the loop, and the current is coming out on the left side and going into the page on the right side. Is that okay? Any question about what I've done? So this represents the current. So the magnetic field generated from that current is circular about the wire. So I'm going to grab myself a circle. And into the page means that I'm trying to make this the same direction as the current in the picture. So am I the same? I'm not sure. Yeah, so based on what I see in this picture here, the current is going into the page there and out of the page on the other side. So I'm trying to match up with that. So everybody okay with that so far? All right, so I'd probably like to make this a little bit bigger. But I want to make it concentric, so something like that. And then, let's see, can I... Yep, I can. So, into the board is going to produce a magnetic field this direction around the current on the bottom right. Everybody okay with that? Out of the board, magnetic field this direction for the current on the left. So a generalized direction of the magnetic field here, that is that way. So if this is the current loop that's on the bottom, at point P where the two intersect, we get a generalized magnetic field that is upward. Everybody agree with that so far? So I'm going to try and use the same picture. To talk about the bottom. So see if I can do that. Well, clearly I did not. Trying to get a handle on all of it at once, but it won't let me do it. But I'm trying. So at the bottom, that's the direction of the magnetic field on both sides of those. So I get a generalized magnetic field upwards at the bottom. Right? I'm just applying the same circle. So whether we're looking at the top one or the bottom one, if this is the top one, it's still causing a magnetic field that's upwards on point P. Is that okay? Or do I need, are you sure? Because you asked. So
Yes,
we good?
yes.
All right. We good?
Yeah, no, I figured it out after much pain.
Okay, much pain. This was not very painful.
Well, no, like this morning I tried to right-hand rule it like 20 times before I could do it correctly.
Oh, I didn't think it was okay. I mean, we could have, just duplicate it and try it that way. Put them both together. They're clearly going to overlap. So we're all good here? All right. The first thing you have to understand about a solenoid is that this is similar to our discussion about a capacitor, in that we have made assumptions about capacitors in order to kind of leave out some details. And one of the things that we did with the capacitor discussion is we indicated that the two plates were very close together compared to how wide they are. This allowed us to ignore edge effects, but it also allowed us to indicate that the electric field on the outside of the capacitor canceled out. Now, it was easier to make that assumption because a plate of charge generated a uniform electric field. We know that a single wire of current doesn't generate a uniform magnetic field. we know that it decays and gets smaller the further away you are from the wire. So we're going to make a similar assumption that the coils are actually very close compared to how wide they are for this analysis, with the understanding that our actual calculation is going to be somewhat an assumption. Now, the truth is, we're going to have some edge effects for a solenoid too, in the same way we have edge effects for a capacitor. So we can get close to the ideal value for the magnetic field produced by a solenoid, but we're not going to be right on top of it. And the wider you make your solenoid and the shorter you make your solenoid, the more the edge effects are going to degrade the size of your magnetic field. There's just no way we can deal with that outside of it. Now, there are things we can do to help increase the size of the magnetic field, and the most likely thing that we would do is manipulate what goes inside the empty space of the solenoid. Just like a capacitor with a dielectric, we can add materials here that will enhance the magnetic field. Now, there'll be new words coming out, and they're not vocabulary words, but we will learn about things like paramagnetic materials. They're like dielectrics, but for the magnetic field. So for the time being, the first thing I wanted you to understand or look at is the magnetic field produced by a single wire. And if we look, there's a circular magnetic field produced by this wire. And the fact that it comes out of the board means the magnetic field is generally to the right on top of the wire and to the left on the bottom of that wire. So I'm coming out of the board. I'm just doing the whole circle thing. It's so much easier. Now on the bottom, same coil. Thumb goes into the board. I get to the right on top of the wire and to the left on the bottom of that wire. Are we okay so far? Now, the first thing you should notice is that every single wire is producing a similar loop of magnetic field. And on the inside, all of that magnetic field is organized in the same direction. Similarly, on the bottom, we are going to have similar organized magnetic fields, all in the same direction, reinforcing the top layer. Everybody following along so far? Now, again, let's follow just one loop for just a minute. Now, these green circles represent the magnetic field produced by this single coil of wire. And I want you to understand that we know it's a circular field, so it extends in the region of space in between the coils, all reinforcing a magnetic field to the right, but it also extends outside of that region to an area of space up here, where the magnetic field is in the opposite direction of the magnetic field produced by the top coil of wires. All right, we're noticing right here that this one's to the right and this one's to the left. Thus, outside the solenoid, the field is being decayed or reduced. But inside the solenoid, the field is being reinforced. The difference, and this is an important difference, is that these aren't parallel plates of a capacitor where the electric field is uniform. We know that the magnetic field produced by the green circles is lower than the ones that are being produced by the single red circle right here, because it's further away from the wire. So, although the field is less outside a solenoid, it's not zero, unless we go to the extreme and state that the distance apart meaning the size of the coils is small compared to how long our solenoid is. So what we will talk about for right now is an ideal solenoid. And then, because I don't want to be, making this up, we'll talk about a real solenoid and what our expectations can be that are different. Does everyone understand that? Real versus ideal. So right now we're going to talk about the ideal. And the ideal indicates that the magnetic field outside the solenoid is very close, if not zero, due to the competing magnetic fields. And that the magnetic field on the inside is uniform due to the reinforcement of the magnetic field from all the other coils. Again, a bit of a lie. It's a stretch. And what we're going to make in the classroom will not easily fit this. But that solenoid that's at the front of the room is a good thing to hold on to and take a look at. It's going to also show what our dependence is. I mean, there's a dependence on current and the loops that determines how powerful the magnetic field is. And we can get that from Ampere's law. Ampere's law will allow us to produce a great estimate for how big the magnetic field is inside a solenoid. Now, to use Ampere's law for this, we need to determine a loop that is likely to help us determine the magnetic field. And this loop might not make sense to you right away, but follow along. We're going to use a rectangle like that. We're going to use this rectangle to determine the magnetic field. And we're going to apply Ampere's law around this rectangle. Okay?
I'm making fun of David.
Why?
Because I used a rectangle yesterday. Like, why are you using a rectangle?
I asked you, why you using that?
I'm just messing with you, David. It's all good.
The reason why a rectangle is helpful in this case is consider the side CD for one. If we're dealing with an ideal circumstance, there's no magnetic field out there. It will not contribute to the line integral. If we consider DA and BC, those two sides, and I'm saying that in that order because remember, we have to integrate around the loop. So side DA and BC also represent portions of our loop. Half of that line is outside the solenoid, so that half will have no contribution to the line integral. But the other half won't have a contribution either, because the line integral is a dot product. And if we consider this portion of the line integral right here, the ds portion would be in that direction, and the magnetic field will be in that direction. So the dot product would require the cosine of 90 degrees, which means there would be zero contribution to the line integral from B to the midpoint, and then there's zero contribution to the line integral from the midpoint out because there's no magnetic field. So by using a rectangle and lining up those sides to be perpendicular to the field, we can cancel out three sides as having zero contribution to the line integral. So remember, this is a sum and has to be a closed loop. So there's A to B, B dot ds, plus B to C, B dot ds, plus C to D, B dot ds, plus D back to A, B dot ds. We have to add all of them together, but these have no contribution to the line integral because their calculation is 0. And it's because we chose the sides carefully so that they would have no contribution to the line integral. We've done this with Gauss's law before too. In fact, this is how we did the infinite sheet. Now I know I'm going to get a question here because I can see the gears turning. So I'm going to hit the pause button. There's no contribution from C to D because the magnetic field is 0. I used only B to C as my secondary example, but from the midpoint onwards, there's no magnetic field, so that portion is 0. And from B to the midpoint, ds and the magnetic field are at a right angle. So the cosine of that 90 degrees is 0, so the dot product eliminates that portion. Because these are all dot products. Okay? And I'm going to use that same logic when going from D to A, because I have half in the solenoid and half out of the solenoid. Which means the only thing I really have to integrate is A to B. And even so, I'm going to use the fact that the magnetic field is uniform inside the solenoid. So for this portion of the integral, I will have B times the integral of ds, which is just the length of the loop. And that's this length, which I'm going to call capital L. This physical length is important and is going to show up here in a minute. So this, of course, has to equal mu naught I enclosed. So has everybody followed this argument so far? Will allow me to go on? Are we all good as where this came from? This is not an unlikely calculation on the exam. They don't show up often, but remember how we showed examples of how to do the Gauss's law for a capacitor? This is doing Ampere's law for a solenoid. So it shows up. So I'm going to go forwards just a little bit. Yep.
Are you allowed to leave an L or does L cancel out?
I'm going to leave it in L. L is not going to cancel out. It is an integral part of the answer.
But don't you decide L?
Yes. But let me get one more step and you'll understand where I have to go next. Okay? So that means the right side is B times L. Right? The length of that single portion of the rectangle is L. So my integral is just that length. Now, the left side has our mu naught in it. I enclosed. Now, if we say that there is a current passing through those wires, the current has to be the same in all of those wires because it's a single piece of wire that's just bent into a helix. So I will be there, but there's multiple loops in there. And to make this applicable to any solenoid, we will just say that there are n number of loops. Now, this part might not be obvious, but let's detach ourselves a little bit. I know I'm writing towards the bottom, but I'm trying to move that over here, and then I'm going to just do that. B inside a solenoid is equal to mu naught times I. Those are obvious things that we would know would increase the magnetic field. But this part might not be obvious. This is the loop density. It represents the number of loops per meter. Sometimes this is written just as a lowercase n, but understand that it's not, the letters we put here are meaningless unless you understand where they come from. So a solenoid's magnetic field is reliant not just on the size of it, but how tightly you pack the loops together. That's the real thing. It's not about how long the solenoid is, and it's not about the number of loops. It's about both of those at once. So pass that around for just a minute. Pull it apart and look at the difference between the two things that are here. You'll notice a clear distinction between the two solenoids that are there. And let's not be all day about it. Just pull the top out of the bottom. And make sure you pass it around so everybody sees it. This is actually a transformer, but it's two separate solenoids, one nestled inside the other. And you should clearly see the difference in the loop density between the two. So in trying to wrap solenoids, we need to find wire that will allow us to increase the loop density. And just take a look at simple numbers here. At best, without melting the wire, we're probably talking about limits of maybe 1 amp in the wire before it's going to start to either get too hot to handle or it's going to begin to vaporize the paint on the outside of the wire. So this value, we can't get away from the fact it's times 10 to the negative 7. Right? 4 pi helps. It makes it times 10 to the negative 6. But you have got to have a huge loop density if you want to get any meaningful magnetic field here. Magnetic fields of a Gauss or less are very difficult to detect. But what if you just want to have a 1 Tesla field? Do you realize using a solenoid how difficult that's going to be? Now, one way to ramp up the magnetic field is to change the permeability. But if you change the permeability, that means you fill the space where the magnetic field is. What if we want to use this magnetic field to do something, to levitate something, to move an object around? Now, I don't want to minimize this. We're going to make solenoids, and your goal is going to be to try and find a way to maximize the loop density. And we'll have a variety of wires that you can use. Our simple goal will be for you to make simple magnets, simple electromagnets. And I have nails and small pieces of PVC pipe, and you're going to try and create a simple magnet to pick up paper clips. And you should be able to clearly show a relationship between loop density and strength of magnetic field. You should also be able to clearly show a relationship between current and magnetic field. You know how to vary current by creating a simple circuit with resistors in the battery. And you know how you can wrap loops of wire around a piece of metal and count. Now, we're going to do it in an anecdotal way. We're not going to get empirical data. You're just going to lift up paper clips and count the number of paper clips you can lift up with your arrangement, change your arrangement, and see how many paper clips you can pick up. It's elementary, I understand. But measuring a magnetic field requires a Gaussometer. I only have a couple, and they are not very accurate. Yes, sir?
There's one of the questions on the homework. It was like a solenoid question.
Mm-hmm.
I think it was like the length. It gave you like the length, and I gave you the diameter of the wire and the diameter of the loops. To find the number of loops, is it like, is the length it gives you how much is wrapped around, or is that how long?
Sounds like they gave you two lengths. They gave you the diameter of the wire and the diameter of the thing that it was wrapped around. But you can only get, if you're going to have a single layer of wire, the closest the wires can be spaced is 1 diameter apart. Right? From center of wire to center of wire is 1 diameter. If you don't know, let me.
Like I'm confused if you like it gives you a length. But I'm confused if that length is used in the.
If what the two of you are saying is the crux of the problem, they're giving you this length, and they're giving you the distance from wire to wire. And you're having to figure out either the loop density or the number of available loops. So knowing this distance and the total distance, you would divide those, the smaller number into the bigger number. That would tell you the maximum number of loops you could fit on the length of tube or whatever. Does that make sense? And you would need that because you're eventually going to need either N over L, where this would be the length of the whole tube, and this would be the number of loops, or you would need the division of those two. Yeah.
So is the diameter of the loops
No, you need that. The diameter of the loop. Oh, you mean this diameter?
Yeah, they need that.
That's probably useless.
Okay.
I think you'll be throwing that information away. Yeah. On it. I always like to take that break, after 15, 20 minutes. You need to, I won't say memorize these, but understand that this is how you calculate the magnetic field inside a solenoid. Real solenoids, though, aren't like this. Real solenoids do not have magnetic fields that are zero outside the solenoid. They leak magnetic field. There's, at least for a moment, you should understand that this is an estimate to the magnetic field inside a solenoid. But there are three things about real solenoids that are not like this. The first is they do leak magnetic field outside, and there's no way not to, for the simple fact that the magnetic field is a closed loop. So there's going to be some magnetic field circling back on the outside of those wires. What's missing from our diagram is kind of the long view, meaning if I go back to my picture here with the solenoid and stop looking at the individual wire, there is a magnetic field that runs through the center and on the outside. Oops. We are trying to make the set of coils close together and long to try and push this portion further away and weaken it on the outside of the solenoid. Okay, I'm sorry, guys, I didn't see your hands. Go ahead.
It's like a little bit back, but can you draw the square, like the bottom of it inside the bottom coil? Like instead of extending down below?
No, if you're asked to draw it on a test, draw it outside purposefully. Okay. With the understanding being, you can draw it close to the edge of the solenoid. Make it outside the wires. Because technically there's a magnetic field inside the wires due to the current, and it's not zero. They want you to this is, the box we drew is a standard. And one of the things about the standard is that we're trying to exploit the ideal system, which has a magnetic field of zero outside the wires. You don't have to be as far outside as I am here, but you need to be outside the wires far enough to understand that we are not in the sphere of the inside the metal of the wires. Okay. So yeah, and definitely don't leave it inside there. Am I good to keep going? Go ahead. You had
Could you just restate the description that they would use to let you know it's